Alright, in this video I'm going to go through some practice problems for the mid-trimester exam for Chem 1B. So there's 20 questions here and there's 5 possible choices for each question, and they all cover the organic chemistry part of the course. So the first question is, what is the hybridization and geometry of the carbonyl carbon in a ketone? So remember, a ketone is where we have a CO double bond and then two R groups, so we call them R and R prime, and so that carbon that's attached to the double bond to the oxygen by a double bond is called a carbonyl carbon, or carbonyl. And for it to make 3 bonds, we must have 3 hybridized orbitals involved in sigma bonds around that carbon. So to get 3 hybridized orbitals, we use one s orbital and we use 2 p orbitals. So you can count them up. 1s and 2 of these p orbitals gives you 3 hybridized orbitals in total. And so this must be sp2 hybridized. So it's either B or C. And then we have to decide whether it's trigonal planar or tetrahedral. So remember, tetrahedral means we have a carbon with 4 things around it that are all equally distant from each other by having this tetrahedral geometry. So to be tetrahedral, you must be sp3 hybridized, because each one of those bonds is using one hybrid orbital of the carbon atom. Whereas sp2 hybridized is where we have a carbon atom with 1, 2, 3 groups around it at equal angles, or roughly equal angles, depending on what it is. And then you've got 1 p orbital that's left over that can then engage in a pi bond. So that carbon atom in that arrangement is sp2 hybridized, and that carbon is planar and has 3 things around it, so we call it trigonal planar. So the correct answer here is sp2 and trigonal planar. Okay, let's look at question 2. Which of the following describes the double bond in an alkene? So the way it's worded, I would say that we're just looking at the carbon-carbon double bond, and the way that carbon double bond is made up is that each carbon atom is making a sigma bond to the other carbon atom using one of its hybrid orbitals. And in each case, it's actually an sp2 hybridized orbital. And so there's one sigma bond, but then there's also a leftover p orbital on each carbon atom, and they are overlapping in a side-on arrangement. And we call that side-on arrangement a pi bond. So there's one sigma bond and one pi bond. So that is answer C, is the correct answer to question 2. Question 3, how should the molecule CH3CH2OH be classified? So this is just ethanol. So we've got an OH group attached to a carbon atom. So that's this one here. And then that carbon atom has 2 hydrogens attached, and then it has a CH3 group. So I'll draw it like that. So the carbon bearing the hydroxyl group has 2 hydrogens and 1 carbon substituent, and that means that it is a primary alcohol. So it has just 1 non-hydrogen substituent, so the answer is A. Question 4, the molecule below has how many chiral centers? So wherever we see a terminus of a bond like that, that's a methyl group, that can't be chiral. Same here. And wherever we see oxygen or nitrogen atoms, they can't be chiral. And wherever we see carbons that are involved in double bonds, they're flat, they're not tetrahedral, they only have 3 substituents, and so therefore they can't be chiral centers either. So the only possibilities would be this one here and this one here. They're the only parts that aren't the end of a line, and they're not part of a double bond and so on. So we need to work out whether there's 3 different groups on each one of those positions. So I'll just rub out those boxes. Here we've got a hydrogen there, and we've also got a hydrogen here that aren't drawn in. So let's look at the right-hand one first. We've got a hydrogen, a methyl group, a amino group, and a hydroxyl group. So there's 4 different groups around that. They're not in priority order. We're not assigning RRS here, so we can just say that is a chiral center. Now if I use a different color here, we've got a hydrogen, a hydroxyl group, an aromatic ring, and then this whole group here is something different. So that's a fourth group. So there's 4 different groups there, so that's also a chiral center. So we have 2 chiral centers, and so the answer is C for this question. Question 5. Which one of the following methods is best for preparing paracetamol? So let's have a look. We've got an amine in this molecule here. And in fact, the left-hand side of all 5 of these answers is the same amino compound. It's para-aminophenol, and it's going to react with something, and really we should be able to spot that if we're going to take an amine and prepare this amide, we must be making this bond here that I've shown in blue. Okay, so when we react with an acid chloride, like in the first example, we're going to get that part of the molecule broken off. And normally we would want to have an R group here, and that would be an acylation of an amine, and this is carboxylic acid derivative chemistry. Now that wouldn't give us the desired product. That would, if that reaction did occur, we would have something that looked like this with a double bond, and then that, and then for reasons we won't go into, that actually really won't occur. Okay, now if we take an amine and a ketone, we're not going to get this acylation to occur. We need to have an acid chloride or an acid anhydride. Those are the 2 species we can use. Same here, we've got an aldehyde. So aldehydes and ketones won't give that sort of acylation reaction. Similarly, here, this is not a happy looking molecule, and it's not the kind of molecule we've talked about in any kind of sense during the course, so that's not going to work. What will work is this molecule here. It's an acid anhydride. It's symmetrical, so I can get the amine attack either one of these carbonyl groups. We won't go through the mechanism, but overall we'll lose the right hand portion here, or the left hand, if we attack the other carbonyl carbon, and we'll end up with the acyl group being this acetate being added. So there it is there, exactly the same group. So the answer here is C. Okay, question 6. Now we're looking at spectroscopy. How many different NMR signals would be expected in the carbon-13 spectrum of cyclopropane carbaldehyde, cyclopentane carbaldehyde? So this molecule over here. So let's count them up. We're only looking at the carbon groups. So here we've got 1 for the carbon that has the double bond to oxygen, so the carbonyl carbon. 2 for this position here. 3, and then 4. And then we've got the question of what about symmetry? Now there's free rotation around this bond here, and that means that over the NMR timescale, we'll see these 2 being equivalent. So this is also going to be our number 3, and these 2 are going to be equivalent as well. So that's going to be number 4. So because of the symmetry of that molecule, we can draw a mirror plane if we wanted to. Don't worry about the fact that one side of this carbonyl group looks like a double bond to oxygen, the other one looks like a single bond to hydrogen. That group is rapidly rotating around, and so on the NMR timescale, we will see both sides of that molecule being the same. We can even also think about that functional group not necessarily lying the way that it's drawn there. It might actually be lying straight up and down, so it would be on the mirror plane. In any case, there's going to be 4 different signals, and so this one, the correct answer is D. Number 7, the index of hydrogen deficiency for C4H6O2. So we should, for a reference molecular formula for this type of compound, we should see CnH2n plus 2, and then oxygen, sulfur, and selenium, we don't see the number of hydrogens per carbon change because the oxygen can just sort of slot into the middle of that chain without changing the hydrocarbon parts of it. So for C4, we should see 2 times 4 is 8 plus 2 is 10. So H10O. And we're actually seeing 6. So we're going to get, in our formula, we're going to have 10 minus 6 over 2. And that is going to be equal to 4 over 2, which is just 2. So the index of hydrogen deficiency is 2, and therefore the molecule with that formula that we're talking about must have either 2 pi bonds or 2 rings, or a combination of them both. So 1 ring and 1 pi bond. Question 8. For the carbonyl functional group in ethyl acetate, to the right here, what would you expect to see an IR band at? Or would you expect to see an IR band at each of the following? So 3000 would be CH bonds. So that doesn't correspond to the carbonyl CO bond, so not that one. 2200 would normally be a carbon-carbon triple bond. We don't have that. That's not a carbonyl group. 1700 is where we'd expect, so around 1650 to 1750. These are very approximate numbers, but around that 1700 range is where we see most carbonyl groups, and it will vary depending on the functional group. So ester will be different to an amide, is different to a ketone, and so on. So that looks to be correct. And then each of these are going to be either CO single bonds or maybe CL bonds for the one around 500. So there's not going to be those. The correct answer is C. That's a typical stretching frequency for a CO double bond of a carbonyl group. Question 9. Which of the following alcohol groups cannot be oxidized with chromic acid? So a primary alcohol can be oxidized with chromic acid. A secondary alcohol can be oxidized. It still has a hydrogen next door. A tertiary alcohol cannot. This is not correct. So chromic acid is an oxidant, so we can't really say that that's the correct answer. And alcohols cannot be oxidized using this reagent. Yes, they can be oxidized with chromic acid. So the alcohol that cannot be oxidized is C, the tertiary alcohol. And remember, the structure of these is something like this, where we have 3 R groups attached to a carbon bearing a hydroxyl group, and there's no hydrogens there. And that's the key. If we don't have any hydrogens on the carbon that has the hydroxyl group attached, we can't do oxidation. Okay, question 10. In an SN1 reaction, that should be number 1, the reaction proceeds with inversion of stereochemistry at the electrophilic carbon. So remember, if we have SN1, we go via a carbocation. So the first step is that we have the alcohol halide. So let's just draw out a simple one like this with a bromine going up, maybe a hydrogen or a second R group going back like that. The first step that happens is we lose that bromide to give us a flat carbocation. And that carbocation can be attacked from either the bottom or from the top by the nucleophile. And so we get a 50-50 mixture of the top versus the bottom attack. And so we wouldn't say that the stereochemistry has been inverted. We'd either say it's been scrambled or it's been turned into a 50-50 mixture of the two possibilities. So overall, the SN1 reaction proceeds not with inversion of stereochemistry. So this answer is false. Question 11. What is the stereochemistry of the molecule below using the Kahn-Ingold-Prelog rules? So we got one stereogenic center there, one chiral center. If we want to assign the priorities, we have hydrogen is always the easiest, it's 4. And then we've got a sulfur is going to be the highest priority, it's got the highest atomic number. And then we've got a carbon versus a carbon. So we're going to have to go one further out along the chain. We look at the one here first, this one on the right. If we look at that one, then it's a carbon that goes to an oxygen, and then it's doubly bonded to that oxygen. So we put in a phantom oxygen atom, and then it's bonded to this carbon atom here. So there's 3 substituents in priority order. Here we've got these 2 implicit hydrogens and 1 carbon of this methyl group. So that carbon is going to go to a carbon, a hydrogen, and a hydrogen as its priority. We look at the first one here, oxygen versus carbon. So this whole side wins. So that's going to be priority order 2. So that's that whole group there is priority 2. And then this group over here is going to be priority 3. Okay, so luckily we've got the lowest priority group at the back, and then we're going from 1 to 2, around to 3 in this clockwise direction. And clockwise is a right-hand turn of the steering wheel when you're driving your car, and so this will be R. So the answer is A, R. Question 12. Which one of the following best describes a carbon-bromine bond of an alkyl halide or a haloalkane? So it is non-polar and possesses no dipole. That's incorrect. So this will be carbon is delta positive versus bromine being electron withdrawing, so that's delta negative. So they'll be polarized and does have a dipole. It is polar. It will be delta positive at carbon, delta negative at bromine. So we've already found our correct answer there, but we'll just check through the others. C, it is polar, delta negative at carbon, delta positive at bromine. So for that to be true, carbon would need to be more electronegative than bromine, but that's not the case. It's the other way around. So that's not true. It is ionic. No, it's not true. It's a covalent bond. And none of the above is not correct. So we found our correct answer is B. Okay, question 13. The reaction coordinate diagram below and to the right describes the energy changes that occur when 2-chloro, 2-methyl-propane and water react together to give the product 2-methyl-propan-2-ol. Which point in this reaction diagram corresponds to the rate limiting step? Okay, so what we're looking at here is what type of reaction. It's going to be an SN1 reaction. And we said that an SN1 reaction has a rate determining step where a carbocation is formed. So the first thing that will happen is that we will lose the chloride by breaking that bond and generate, in this case, a very simple, draw that out again, a very simple carbocation with 3 methyl groups attached to a central carbon that bears the positive charge. Okay, so that's going to be the rate determining or rate limiting step. Now that carbocation is here. It's at position C, where we've gone up through a transition state and then down to a slightly lower energy species, which is this carbocation. And so the rate limiting step will be going from A to B, and the transition state will be B. So we'll be going from A to C, and the transition state for that will be B. So which point on this reaction diagram corresponds to the rate determining step would be point B, getting to that high energy transition state on the way to the carbocation. Question 14. Which of the following best describes the geometry around this carbon-carbon double bond in the alkene below? So it can't be W, R, or S. It must be E or Z. And the thing we need to do here is apply those Carnot-Gold-Prelog rules. So what we have to do is split the molecule so that we look at one of the carbons of the double bond and assign priority 1 and 2, or higher and lower, and then we look at the other carbon of the double bond. So we're going to split the molecule like this and look at just one of these carbon atoms at a time. So this carbon atom here on the right, we've got a carbon versus a carbon. So we need to go further out along the chain. We've got an implicit hydrogen here, so we're going to go from highest to lowest priority out of those substituents. So we've got a sulfur atom, a carbon atom, and a hydrogen. So our carbon there will go to sulfur, carbon, and hydrogen. Now on the other side, let me do this in a different color actually. So we'll do this one in red. It goes with a double bond to oxygen, and then to this carbon here. So to carbon. So it's a double bond to oxygen, so we draw in 2 oxygens because there's one of them as a dummy atom. And now we compare these two. So how do these two compare? We go from highest priority on each and we look for the first point of difference. So we've got a sulfur versus an oxygen. Sulfur wins. So this whole group here is the higher priority. So let's give that a 1 and give this down here a 2. And now we look at the other carbon of the alkene. So looking at this carbon atom here, look at the two things that are bonded to it. Firstly, one substituent is an oxygen. So we've got that as an oxygen versus here we've got a carbon. So it's carbon versus oxygen. And immediately this one wins. Oxygen is the higher priority. And so this will be the number 1 group and this will be the number 2 group. Okay, now we've assigned priority higher and lower to each of the carbon's substituents. Now we look at the highest priority groups on the same side or on opposite sides to each other. So now we're looking at the molecule in a different way. We're going to look at the molecule being split along a plane this way. And we see that the two highest priority groups are on the same side. They're on the same side. So that's going to be the Z isomer. So the correct answer is B, Z. Question 15. Which of the following is a nucleophile? So a nucleophile is something with an excess electrons, and it's going to be seeking out a nucleus with a positive charge or a source of partial positive charge. So if we look at A, we've got CH3SH. Sulfur has lone pairs of electrons, and with it being one row below oxygen in the periodic table, it actually makes it more nucleophilic because it's more polarizable. It's holding on to its pairs of electrons less tightly. So it's actually a very good nucleophile. So that gets a tick immediately. Something with a positive charge like this compound here, this is a carbocation, that is not going to be a nucleophile. It's got a deficiency of electrons. It's going to seek out electrons and be an electrophile. Which of the following is a nucleophile? We've got hydroxide has a negative charge and lone pairs of electrons. So it is going to be a very good nucleophile as well. And chloride has negative charge and electrons as well. So it's going, if we draw it down here, it's Cl. Halides with a negative charge have 4 lone pairs of electrons and a negative charge. So it's going to have the ability to make a new bond by sharing that pair of electrons with an electrophile in a reaction. So this one is E. All but B are nucleophiles. Okay, question 16. What is the IUPAC name for this molecule? So firstly, we want to find the longest chain. So we'll just arbitrarily start numbering here and work our way along the chain like this. Now, can we find any other way to number this that's better? I can immediately see that this carbon here and that carbon there have other groups attached to them, but those groups are no longer than what we've already got in our chain. They're only 1 carbon groups, and our chain only goes 1 extra carbon, so that means that there's no reason to number this any other way. So it's going to be a 6 carbon molecule, or a hexane, and it has methyl groups at the 2 and the 5 positions. So it's going to be they're both methyl groups, so it's going to be a dimethyl hexane. And they're at the 2 and the 5, so it's 2,5 dimethyl hexane. So if we look at that here, this one here. I would normally write that without that space in the middle there. So that's just a minor detail. Okay, question 17. What is the product of the following reaction? We've got an alkyne, and we're reacting it with hydrogen and a palladium catalyst. Now, if the catalyst was something called Lindlar's catalyst, that would convert that part of the molecule to an alkene like this with extra hydrogens on it and the hydrogen we already had, and then that aromatic ring. However, it doesn't say Lindlar's catalyst, it just says palladium catalyst. And so when we form that alkene, it will actually add an extra set of hydrogens across that double bond there. And so we would end up with 2 hydrogens here and 3 hydrogens here attached to that aromatic ring. Now, aromatic rings don't react with hydrogen and palladium because they're stabilized by aromaticity, which is a special thing governed by Huckel's rule, 4n plus 2 pi electrons. And so this part of the molecule does not react with the hydrogen with this palladium catalyst, so it's unchanged. So we should see just an ethyl group attached to an aromatic ring, which is answer B here. Answer A is what you would get out of Lindlar's catalyst, where we can stop at the 1 lot of hydrogen being added. Answer C is just move one of the double bonds out of conjugation, so it's no longer aromatic. That would be bad. Answer D, we've hydrogenated all of the pi bonds, which is quite difficult to do with an aromatic system because the aromatic rings are stabilized by aromaticity. And answer E doesn't really make any sense. Okay, question 18. Aromatic molecules react principally by which type of reaction? So because of the stabilization of aromaticity, we see aromatic rings want to keep their aromaticity, and so they don't do addition reactions. If you did an addition reaction across the pi bond, you would lose their aromaticity. That's what we see with alkenes, because the alkene pi bond is relatively weak, and replacing with the strongest sigma bonds is good. So we don't do addition reactions. So it can't be B, and it can't be C. We don't normally do nucleophilic type reactions. Certainly, we haven't talked about any in this course. And we can't do SN1 reactions because we can't form stabilized carbocations. So the answer here is electrophilic aromatic substitution. So aromatic rings will react with electrophiles through a substitution mechanism whereby they can retain their aromaticity. Question 19. The addition of electron withdrawing groups to an aromatic ring of a phenol will make it more acidic or increase its acidity, decrease acidity, will not affect the acidity, will make the phenol change color, or make the molecule more reactive. So increased acidity is the correct answer here, but let's talk about why. If we have a phenol, so we can draw it out like this, and then we lose a proton, so we go to the phenoxide, like that, then if we have electron withdrawing groups, say X here, that can help to stabilize that conjugate base form of the molecule, or of the phenoxide. So electron withdrawing groups will help to stabilize the conjugate base, so they increase the acidity of the conjugate acid that we start with. So it's not B, and it's not C, so it will affect the acidity. Now D and E are a little bit more subjective, but make the phenol change color. Well, we don't know what the structure of the particular phenol is we're talking about. In general, we don't know whether it will have an effect on the color of the phenol until we know what the structure of the phenol is. Similarly, we don't know how it will affect the reactivity of the phenol. We're talking about the reactivity of the phenol towards acids, towards bases, towards nucleophiles, towards electrophiles, towards hydrogenation, or what kind of reaction are we talking about? So putting electron withdrawing groups on may make it actually less reactive in many situations. Okay, so the answer is A. It will make it more acidic. Another way of saying that is that it will lower the pKa. So for example, if the pKa was 6, then it might go down to 4 with electron withdrawing groups and so on. Question 20, last one on this practice quiz. The molecule below contains the following functional groups. So let's have a look. We've got an aromatic ring. We've got an ether. So we have two R groups attached to an oxygen. We've got an amide, which is a nitrogen group attached to a carbonyl group. We've got a ketone, and we have an aldehyde. So the aldehyde must have this hydrogen here. The ketone is where we have R groups either side. So there's our R groups. Just get rid of those. So we've got quite a few functional groups. Let's have a look what we've got in the answer. Aromatic ring, yes. Ether, yes. We've got an amide, yes. And we've got an aldehyde. So already A is looking good. B, aromatic ring. Ester, we don't have an ester. C, aromatic ring, yes. Amine, no, we don't have an amine. We've got an amide, this one here, because we've got a carbonyl group attached directly to the nitrogen. So it's an amide, not an amine. We don't have any non-aromatic rings, so that's not correct. E, we've got an aromatic ring, we've got an ether, we've got a ketone, we've got an amide, and we have an aldehyde. So I think that's the more correct answer because we've covered more of the functional groups. Question A is missing one of them. It's missing the ketone. So I think answer E is the correct answer to this question. Okay, hopefully you found that useful in going through your answers to this practice question, and good luck with the mid-trimester exam.